All right, ladies and gentlemen, the purpose of the lecture you're about to look at right here is to fill in some more information about the process of writing electron configurations. We'll also be discussing during the course of this lecture uh, the shortcuts we can use when writing electron configurations, and also we'll be looking at the formation of ions from a perspective of what's happening with our electrons. So, as you're going through to look at this lecture, please have out a couple of different resources. If you can please get out your Aufbau process sheets that we handed out to you in class. And in addition to that Aufbau process sheet, if you could also please have out your periodic table. Both of those tools will be of great assistance to you in completing the lecture. And without any further ado, let's begin. What I'd like to look at here is a couple of electron configurations for different elements on the periodic table and see if we can develop a new way of looking at this table with respect to those electron configurations. So let's go ahead and start with the group 1 on the periodic table, that is the alkali metal family here. Starting in the upper left-hand corner there, if we look at hydrogen, the electron configuration for hydrogen, our simplest element on the periodic table, with just one proton and one electron, would be in its ground state a 1s1 configuration according to your Aufbau process sheet there, where the 1s orbital is the lowest potential energy position that electron can occupy. So this would therefore be a 1s1 position for the electron in the hydrogen atom. Let's move down now to look at the next alkali metal in that family. Lithium is the first of our what we traditionally consider to be the alkali metals there. Lithium has 3 total electrons. And with 3 total electrons, we would expect an electron configuration, following your Aufbau process sheet, of 1s2, followed by, in the 2s orbital, a 2s1 configuration. And kind of moving down through the rest of that family, we can move on to sodium. Sodium, with its 11 total electrons, would end up with a configuration of 1s2, 2s2, 2p6, 3s1, and then just for giggles here, let's do one more. Potassium, the next one down. Potassium, we're all the way up to 19 total electrons now, and with 19 total electrons, that would give us a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And something you might notice in common here among all of these electron configurations for these group 1 elements is that it seems all of them end with an electron configuration of s1. Hydrogen ends in 1s1, lithium in 2s1, sodium in 3s1, and potassium in 4s1. Which means we've kind of developed here a little bit of a pattern. Looking at the alkali metal family here, we could then predict the last filled orbital for the rest of the electrons, for the rest of the elements within this family. Continuing down, lithium was 2s1, sodium was 3s1, potassium was 4s1, and then moving down further, we would expect rubidium to therefore end in 5s1, 6s1 for cesium, and 7s1 for francium. And I can kind of generalize then that the alkali metal family are all going to end with an electron configuration of what we refer to as ns1, where n represents the principal quantum number that is essentially in this periodic table here, the period on the periodic table. So that would be n is 1, 2, 3, 4, 5, 6, and 7 going down. So that's a nice kind of pattern here. Allows us to make some predictions about that alkali metal family. Now let's take a look at the same sort of idea, but instead for the alkaline earth metals. Looking at my alkaline earth metals, the first of those alkaline earth metals on our table is beryllium. Beryllium, whose electron configuration is 1s2, 2s2 for our 4 total electrons in the beryllium atom. And then going down below beryllium, we next end up with magnesium. Magnesium, which is element number 12 on our periodic tables. Magnesium with 12 electrons would occupy an electron configuration of 1s2, 2s2, 2p6, 3s2 in its ground state. And I think you guys can probably predict where this is headed. Down to the next one for calcium. Calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2 to bring us up to our total of 20 electrons there. And again, we notice the pattern that all of these alkaline earth metals appear to end with an electron configuration of s2. So we could therefore state that the last filled orbital here, the electron going to the last filled orbital there, would occupy the position of ns2 for all of those alkaline earth metal species, where again n is the period on the periodic table. All right, so we've got some nice new patterns here. Continue along. Let's take a look at, let's move over to, let's say, boron, element number 5. Boron with 5 electrons has an electron configuration of 1s2 and then 2s2 following your Aufbau sheet. And following the 2s orbital, our last electron would go into the 2p1 position there. So it looks to us here like this is 2p1 for our last highest energy electron within boron's electron configuration. And immediately below boron, we find the element aluminum. Well, again, we'll go through one more here. Aluminum with a total of 13 electrons would be a configuration of 1s2, 2s2, 2p6, 3s2, 3p1. So again, aluminum would be the highest energy electron within that configuration of 3p1. You guys can kind of imagine now the rest of that family should be occupying the p1 orbital, so all of those boron family elements are occupying a p1 orbital. Now, moving along to the next one, right next to boron, element number 6 comes after boron, which is carbon. And looking at this, if boron was 1s2, 2s2, 2p1, carbon with one more electron would simply be the same configuration, but instead of the 1, they would now be 2 to make that into carbon. So for carbon, that would be a 2p2 highest energy electron. You can imagine going through the rest of that period 2 there, we would be filling up the rest of that p orbital, which means we'd be looking at 2p3, 2p4, 2p5, and 2p6 for the highest energy electrons in the remainder of that second period. So if we're going to be generalizing here then, we could state that all of these electrons within this portion of the periodic table would be filling an orbital, which is in the what we refer to as npx position, where n represents the period on the periodic table. So for these second row right here, we're in period 2. The p is the shape, again, the dumbbell-shaped orbital. And then the x position represents how many atoms into that what we refer to as the p block we are. So 1, 2, 3, 4, 5, and 6 as you move across. And using that logic again, we can make a prediction that the element which is found right down here on your periodic table, that is the halogen in period 4, that being bromine, that halogen in period 4 should occupy a position with the highest energy electron of the 4th period in a p orbital, the 5th electron into that p block, so a 4p5 position. Now there's one little outlier that we just kind of hit upon right here, and that is this guy up in the upper right-hand corner right there, helium. Helium, you recall, is not a p block element because in the first energy shell, there is only an s orbital present right there. So we're going to go ahead and look at this position right here for helium. Helium gets a configuration of 1s2, which really means, in fact, that it could kind of belong, logically, if you were shaping our periodic table this way, with the alkaline earth metals. However, we're going to put it over here with the noble gases because it behaves most similarly to a noble gas in that it has a completely filled valence shell of electrons and therefore is relatively non-reactive. So we're going to put it over there with the noble gases here, even though its electron configuration looks more similar to the alkaline earth metals. All right, so we've gotten through most of our periodic table now. There's only 2 more positions here, and interestingly enough, you can kind of start to see some kind of magic happening in terms of your electron configurations. If you think about it here, guys, on your Aufbau process, as you've been going through and filling these orbitals, you remember that the d orbital can be filled with a total of 10 electrons at a given potential energy level. because we have 5 subshells, each of which hold 2 electrons spinning in opposite directions. And amazingly here, looking at your periodic table, the transition metal family right here in the center of our periodic table, that transition metal family has in it 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 elements as you go across, which implies what we're really looking at here within the transition block here is what we refer to as D-block elements. Now, something you want to watch out for, though. If you look on your Aufbau sheet, you'll notice that the first d orbital is actually in the 3d position, which means these atoms in the first row of the transition metals are filling the 3d orbital even though they're in the 4th period of the periodic table, which would imply, therefore, the last filled orbital within this d block should not be the ndx position. It should really be the n-1 dx position. Which means if we were making a prediction right here about the element that I've kind of starred here on the periodic table about what would be the highest energy electron present within the electron configuration for this atom in its ground state, we look at the period for this element. It is period 6. It's in the d block, and it's the 3rd atom into the d block, which would imply that that highest energy orbital electron should be in the n-1, which would be the 6-1 or 5d3 position. And we're going to apply that same sort of logic to the lowest elements on our periodic table here, down the very bottom right there. Those two that we kind of pull out by themselves, 2 rows here, the actinides and lanthanides are inner transition metals. Those actinides and lanthanides, not surprisingly, have a total of 14 electrons going across, and those 14 electrons are the 14 f orbital electrons from your Aufbau sheet. So this is what we refer to as the F block on your periodic tables. Here you have to be very, very careful, because remember that F block, the first f orbital electrons off of your Aufbau sheet, are found in the 4f orbital. And the F block, if you recall, we pull it out down at the bottom of the periodic table because it really should go kind of right in here on your periodic tables after the lanthanides, element number 57. So really the F block really should be inserted right in here on your periodic table, meaning really the F block here is really part of periods 6 and 7 on your periodic table. The lanthanides being part of period 6, the actinides being part of period 7. And we've only pulled them out there just to save some space to make it so that our periodic table isn't incredibly wide. Now, that being said, that implies then if the first f orbital to be filled is the 4f orbital, and we are in period 6, that would mean that generically the f block electrons being filled here are filling the n-2 fx position. All right, so at this point here, guys, you can kind of recognize how it is that we were so able to rattle off a really, really long electron configuration without actually looking at the Aufbau process sheet. We haven't gone through and actually memorized all these electron configurations. That would be a waste of time. Instead, what we've done is we've actually memorized the pattern. So let's say, for example, here that I wanted to look at, let's call it this element right down here. That element in the 6th period for our 2p position is lead, element number 82. Rather than going through and trying to count up 82 electrons in my Aufbau process sheet, which would be an enormously painful process, which we've already had you guys do a couple times, instead what I'm going to do is I'm just going to literally read this electron configuration off of the periodic table, starting at the very top, again, Aufbau from the ground up. So for lead, I would go 1s, 2, followed by, in the 2s orbital, 2s2, followed by 2p, 6, followed by 3s2, 3p, 6, reading down next to the 4s2, And how here we have to be a little bit careful. Moving into our D block, recall the D block electrons are in the n-1d position. So if I'm in the fourth shell, this is now the n-1 or 3d 10, 4p 6, followed by 5s 2, n-1 would give me 4d 10, 5p 6, followed by 6s2, and here you have to be really, really careful. Followed by 6s, remember here I'm in my lanthanides now, because that's where the lanthanides should come in, down to n-2, which would be 4f14, back up to the transition metals, followed by n-1 is 5d 10, and then here I'm at the very end here. I'm now back into the 6p orbital, and I'm the second one in here for lead there, so that would be 6p2. So again, instead of going through and following that outbound sheet here, trying to count up electrons as I go, I could simply just read it off looking at the table. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p2. And that's literally as easy as it is. So let me kind of go back here and get rid of some of the green on our screen here, tidy this up a little bit for our final notes. And let's go ahead and now take a look at another couple ways to make this whole process of writing electron configurations easier. So now that you can see that your periodic table is really a direct reflection of the electron configuration in terms of the shape of that table, let's make it even easier. You might have noticed here as we've been going through and writing these electron configurations that we follow the same process every single time. That is, it's always 1s2, 2s2, 2p6, 3s2, and so on and so forth. And all those atoms, past a certain point, all have the same configuration up until the very last part, which is what makes them different from what came before. So rather than going through and writing that entire configuration out every single time over and over and over again, we're just going to recognize that it follows the same pattern. And so rather than writing the whole pattern every single time, we're just going to focus on what comes at the very end, which is really what distinguishes that element from all the others. So we're going to refer to this as what we call our noble gas shortcut. We're going to request that you only use this shortcut for elements that are in period 4 and above, that is, elements with an atomic number greater than 18. So let's go ahead and show you how we're going to do this process. Find tin on your periodic tables. Tin is element number 50. Element number 50 on your periodic table is found in the P block, right down here. So here's tin, is in the 5th period, second element, and in your P block. So looking at tin, element number 50, we can now go ahead and write its electron configuration using our periodic table as our guide. Starting at the very top, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and -1 gives me, careful here, 3d10, 4p6, 5s2, and -1 gives me now 4d10, followed by 5p2. So let's go ahead and again write that whole thing out on our next slide here. And again, that configuration was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. So, huge configuration, pain to write. And let's go ahead and focus now on this trick with what we call our noble gas shortcut. What I want you to recognize here is that if you look at the configuration starting at 1s2 and ending right here at 4p6, ending at 4p6 on our periodic table is ending at this position right here. That is the noble gas previous to tin that we've passed. That noble gas is krypton. So krypton's electron configuration really is this right here. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. So what I'm going to do to write this now as a shortcut is to simply put in brackets the element krypton showing its configuration represents all of that in the brackets up above, and then we're just going to focus on what comes after that noble gas, which is 5s2, 4d10, and 5p2. And the reason why I really like to do this, besides the fact that I recognize that this is just a pattern, and because of that pattern repeats the same way every single time, I've just saved myself an inordinate amount of time by doing that. The other thing that really is important about this is that what I see here is, after the following noble gas, I end up in the 5th energy shell, which is the highest energy shell of electrons. So by using that noble gas shortcut, what I've really focused in on here is the position of the valence shell electrons. So within this configuration, I've still written the valence electron configuration here, giving me 4 total valence electrons, which tells me really the most important electrons in terms of chemical bonding within this sample. So from here on out, guys, you're certainly free to use this noble gas shortcut, just bracketing the previous noble gas and then writing after that noble gas all the stuff that remains in order to complete your electron configuration. So we'll do one more quick example here. Let's take a look at the element francium. Francium is an enormously large element down at the very bottom of the periodic table, element number 87 in the bottom left-hand corner. So francium is this one right over here. And seeing that, in fact, this is the position of francium, I could go through and write out an enormous electron configuration, or, alternately, I could just use the noble gas shortcut. The previous noble gas to francium is this position right here. That is element number 86, which is radon. So following radon, the only electron in the electron configuration after radon would be moving down to that right here, the 7s1 orbital, which implies, therefore, the electron configuration for francium is as simple as radon's electron configuration followed by 7s1. And that just saves us a huge amount of time. Now we know the valence electron shell configuration. Now we can use it to predict behavior of francium. All right, so again, go ahead and use that noble gas shortcut from here on out, rather than writing out that whole mess. If you want to do the whole mess out there, you're certainly welcome to do so. But I would say, let's just skip that whole mess and recognize the shortcut is way, way faster. All right, so last but not least, there are a couple more things we need to, actually not last, I guess, a couple more things we need to discuss. Go ahead and find for me, please, on your periodic tables, copper element number 29. So copper is element number 29 on your periodic tables. And as it turns out, copper is right here on your table. So here is copper. And let's go ahead and write its predicted electron configuration. And you're certainly welcome to use now its noble gas configuration. The previous noble gas before copper is right here in this position that I've marked with the green star, that being argon. And following argon, we will move into the 4s orbital, so it would be argon followed by 4s2, followed by, and minus 1 would give me 3d9. So looking at that here, it should give me again the configuration argon, 4s2, 3d9. And that sounds great in terms of our prediction. However, if you can take a look, please, at your periodic table, you'll notice that those periodic tables of the elements actually give you the electron configurations for these atoms. So find for me, please, copper on your periodic table. and then look underneath the symbol Cu on the front side of your periodic table there. Immediately below there, you'll see it listed with an electron configuration. And listed right there for you on your periodic table, it says, well, actually on your table, it says argon 3d10 4s1. Now, the first thing I want you to notice here, guys, is that your periodic tables write these electron configurations out of Aufbau order. I apologize, guys, if they do that. Most chemists in the planet will actually go through and write the sequence of electron configurations in Aufbau order, that is from the lowest energy to the highest energy. So in that case, 4s should come before 3d. However, your periodic tables, for some reason, actually write them organized by principal quantum numbers. That is, they organize all the 3's before all the 4's. So I would like you to, for your test, continue using the Aufbau order. So again, guys, you're not simply allowed to just simply copy off the electron configurations off your periodic table, because they will not give it to you in Aufbau order. We will require you to do so. But what I do want you to recognize here, guys, is this. There's actually not just a difference in terms of the order that they write these things, but there's really a difference in where the electrons are actually found. That is, we have only one 4s electron and 10 3d electrons. And the real question is, who is correct? Your periodic table or the prediction we've made using the Aufbau process? And the obvious answer here, guys, is that the Aufbau process is a guideline for relative potential energy of orbitals, but sometimes, just due to the nature of the electron configuration and the actual position where those electrons occupy relative to one another, sometimes it can actually be energetically more favorable to put an electron in a different position than the Aufbau order would predict, because that just might move the electron further away from other electrons within the atom, and therefore put it at a lower potential energy level. And the real trick is there's just some places where there's some exceptions to that Aufbau rule. In particular, these exceptions tend to happen within the d block and the f block of electrons, and that kind of makes logical sense, because if you remember way back to the Aufbau diagrams we did at the very start of our discussion of electron configurations, the difference in potential energy between those d block electrons and the electrons that come immediately after them in the p block or in the s block tend to be very, very small differences in potential energy. Whereas looking at the very start of the periodic table, when you moved from like the 1s to the 2s orbital, there was big gaps in potential energy between those s orbital positions. So generally, what really happens here is by filling up the electrons into the d and the f blocks, sometimes you can just move an electron slightly further away from its neighbors by putting it into a different shaped orbital, and that minimizes repulsion between electrons and therefore puts it at a lower potential energy. So we aren't going to be able to, with the math which we do in this class, predict when that's going to occur. We just recognize that, in fact, it does occur sometimes. And we can know where to look for it. So in general, when you're looking on your periodic table for places where exceptions are likely to occur, those exceptions generally occur right before you have a fully filled d block. So elements right in here tend to be exceptions. There's also a couple other places where you find exceptions right there. In particular, you might look at, say, nickel right next to it right here. Nickel is another exception right here where you've got actually a predicted configuration of 4s2 3d8, but the actual configuration is simply 3d10. The other place where we tend to find some exceptions is where we are about to see a half-filled d orbital. So I would always kind of tend to look for places around in here, places around in here for exceptions. And then unfortunately, the entirety of the f block is kind of a mess. So all of this down at the bottom right here are places where you want to look for those exceptions. In particular, take a look at the actinide series here. The actinide series, remember, really starts right up here, the position where those actinides should begin. So if you look at element number 89, actinium, actinium's electron configuration is exactly what you would expect it to be based upon its position. Its highest energy orbital there is a 6d1 electron. So this is filling 6d1 right here. But then moving along, after actinium, we move down to thorium, which is 7s2 6d2. And again, that's a 6d electron, whereas we would have predicted, based upon our position, that we should be in the f block right now. And then we move on to protactinium, which is 7s2 5f2 6d1. So now we've got kind of a mixture of f and d orbital electrons there. Uranium is 7s2, 5f361. Neptunium 7s2, 5f461. Plutonium skips all right to 7s2, 5f6. And then we move on kind of filling that f orbital throughout the remainder there. So all the places kind of along through here, just watch out for them. This is places where double checking the actual real electron configuration is going to be valuable to make sure that you aren't making a mistake based upon the Aufbau sequence of our rules there. So again, the actual electron configuration that atoms take is more important than whatever prediction we would make based upon our Aufbau sequence of rules. So always make sure you double check your periodic table, which you will have as a resource on your test when writing these electron configurations. All right, so we've talked about noble gas shortcut. We've talked about the exceptions to the electron configurations. Last topic of conversation for this lecture is to determine the electron configuration of an ion. If you remember from our discussions earlier, we've talked about the existence of ions as being species which have a net charge. Now, those atoms, in terms of forming chemical bonds, can tend to either gain or lose electrons, either as a result of absorbing energy during a process, like you could absorb, say, a photon of light and excite an electron to eject it, kind of similar to the photoelectric effect, or we could transfer electrons during the course of a chemical reaction. And anytime you start to remove or add electrons from what had originally been a neutrally charged atom, what you're going to end up with is something that has a net charge. And those atoms which have either gained or lost electrons, we refer to those atoms as ions. And in general, atoms on the periodic table tend to gain or lose electrons during chemical reactions in such a way that fulfills what we refer to as the octet rule. We'll be talking about this octet rule more in our naming and bonding unit. But for right now, just recognize here, guys, that there's a general tendency for atoms to gain or lose electrons in such a way that they end up with a filled valence shell of electrons. We call that filled valence shell a complete octet, a set of 8 electrons. And we recognize that that octet, the 8 electrons total, comes about as a result of the fact that within the highest energy shell of electrons, we end up with electrons in the s orbital, which contains 2 electrons when completely filled, and the p orbital, which contains 6 electrons when completely filled. So combining all those s and p orbital electrons gives us a total of 8 in any given valence shell, with the exception of period 1, where there's only s electrons present. Now note here, guys, that the d and f electrons never get included within the valence shell because those d and f electrons are found in the n-1 dx orbitals, or the n-2 f orbitals, recognizing then that we're never in the highest energy shell, we're always in the -1 or -2 position from that highest energy shell when we've got d or f orbital electrons. So what we're going to do here now is we're going to make some predictions about the formation of ions in order to fulfill this octet rule based upon the electron configurations of a couple different species. So let's go ahead and take a look at, let's say, sodium here. Sodium as an alkali metal is element number 11. Find it, please, for me on your periodic table. Symbol is Na, and we've got 11 electrons in that sodium atom. Let's go ahead and write its electron configuration, following along on your periodic tables. For sodium, it is 1s2, 2s2, 2p6, 3s1. So that's a sodium atom. Now, if you remember from our discussion of periodic trends, sodium atoms are really, really big atoms on the far left-hand side of the periodic table. And because those atoms are really, really big, they have loosely bound valence electrons. That is, their electrons in the highest energy 3s shell are a long ways from the nucleus. They're not very tightly held onto. And as a result, that sodium is going to have a tendency to lose that 3s electron to a more electronegative element during the course of a chemical reaction. So if we were to give up that 3s1 electron, that would imply that as it loses that electron, sodium's new electron configuration would now be 1s2, 2s2, 2p6, 3s0. That's all that we have left. And we recognize here, guys, that in losing that 3s electron, we've now fulfilled our octet rule because sodium now has a complete valence shell. That valence shell, the outermost shell of electrons, now being the second energy shell with 2s and 6p electrons. We fulfilled now our octet rule of 8 electrons in its outermost shell. Now for sodium, we're unlikely to lose any more than that one 3s electron, because if we did take away another electron, it would now be coming from a 2p orbital, which is much closer to the nucleus and therefore bound much more tightly. It's not as an attractive target to be picked off by another more electronegative element. And in looking at this now, sodium, which had a total of 11 protons, as an ion, has now formed an ion with a total of 2 plus 2 plus 6 for 10 total electrons. And if we had 11 protons and 10 electrons, that implies now the sodium atom has one more proton than it has an electron, and therefore it has a charge overall of +1. So we say the sodium ion has a charge of +1 due to its electron configuration of 1s2, 2s2, 2p6. And again, remember, it's positive because the electron it lost was a negative charge. Losing more negative makes you positive. All right, let's take a look at one more example here for the formation of another ion. Have a look and find for me, please, oxygen on your periodic table. Oxygen is element number 8, and we can predict, based upon its position there on the table, an electron configuration of an oxygen atom of 1s2, 2s2, 2p4. And that's a total of 8 electrons there as a neutral atom. Now, oxygen, unlike sodium, is on the far right-hand side of the periodic table. And as an element on the far right-hand side of the periodic table, it is small and electronegative, therefore it's able to get very close to other atoms to steal their electrons away. So during chemical reactions, oxygen has a tendency to gain electrons rather than lose them. And if oxygen was going to be gaining electrons in order to complete the octet rule, we would have a prediction that it would form a nuclear electron configuration as it gains electrons of 1s2, 2s2, 2p6. And now with those 2 electrons in the s and 6 electrons in the p orbital, we've got a total of 8 electrons total in oxygen's valence shell, completing its octet rule. Now again, we're unlikely to gain more than 2 electrons for an oxygen atom, because if it were to gain more than 2 electrons, those new electrons would have to now go into the next energy shell, which would be the 3s1 shell, putting them farther from the nucleus of the oxygen atom, and therefore at a very high potential energy level. So again, to lower the potential energy of those electrons, in general, we're going to put them in their lowest potential energy positions, that is closest to the nucleus as possible, which gives oxide ions a configuration of 1s2, 2s2, 2p6. Given that oxygen had a total of 8 protons, and as an ion, its electron configuration had a total of 2 plus 2 plus 6 for 10 electrons, the overall charge now on the oxide ion would be -2, recognizing that it has 2 more negatively charged electrons as an ion than it has positively charged protons. And at this point here, guys, you should now be able to make predictions about the configurations of ions of these various elements on the periodic table based upon their position and tendency to fulfill the octet rule. Now, as it turns out, this ability to determine ion configurations is going to be very, very important when we move on to bonding and naming during our next unit. So, that should complete right now for us our discussion of electron configuration details. Thank you very much for listening.